All right, I think it's recording now. Okay, so the definition of heat is it's the energy transferred into or out of a system. We're going to use Q for our variable for heat. And we're going to say that when Q is positive, a system gains energy. And if Q is negative, the system loses energy. So if I say we had to transfer 1,000 joules of energy to warm up a cup of water, then in that case, we added energy to the water, the Q would be positive 1,000. But if I said, how much energy do you have to take away from water in order to make it freeze? The answer would be negative 1,000. So taking energy away from a system is negative, Q is negative, and adding energy to a system, Q is positive, okay? Now, here's what part A of your lab should have looked like. So I don't think anybody finished their lab because we kind of put a pause on part C, right? So I'm going to kind of show you here. You can go back to the slide presentation, take a peek, and make sure yours looks like this. But this is kind of what you should have from lab part A. You change the amount of energy you added to the cup of water, and as you added more energy, the temperature went up. You should have found that you got a straight line the way it was, which means that the change in temperature is directly proportional to the energy added. So because you got a straight line that went through 0, 0, the conclusion is that the change in temperature is directly proportional to the energy added. That should be your conclusion. Your math model should look like this. On the y-axis, you have the change in temperature, delta T. That equals the slope, 5.98 times 10 to the negative fourth, times what's on the x-axis, which is Q. So for part A, that's pretty much what you should have right there. And if you don't, you can go back and touch that up before you turn it in, okay? We're going to have some time today to work on that. So what we found was how much the temperature of the water changed is directly proportional to the energy we added. Now, in part C of the lab, which you're still going to do, so that's what we're going to work on today here. I'm just going to give you a preview. What you're going to find is that as the mass of the water goes up, how much the temperature change goes down, which kind of makes sense, right? If you were to microwave a little itty-bitty cup of water for 10 seconds, it'd get pretty hot. But if you had a huge bowl of water for 10 seconds, you'd barely notice it, right? The bigger the mass, the smaller the change in the temperature. So those are inversely related. So what's going to happen is, to get a straight line, we're going to plot 1 over the mass. Oh, my pop here. Down at the bottom there, you're going to plot 1 over the mass on the x-axis. On the y-axis, you're going to plot the change in temperature, and you should get a straight line. Your slope might be slightly different than mine because I did mine for 15 seconds. Maybe you did it, maybe you'll do a different time. It doesn't matter. And then our math model will be that y, the change in temperature, equals the slope, whatever you get, times x. And x is 1 over m. Okay? That's going to be your math model. And when that happens, our conclusion is that y is inversely proportional to x. So we will say y, the change in temperature, is inversely proportional to x, which is the mass of the water. So that's what part C is going to look like, okay? So you can come back and check that too after you finish it. Now, I'll come back to part B in a minute. So what we know so far is that how much the temperature changes depends on how much energy we add, and it depends on the mass of the water. There's one more thing that it depends on. So there's my summary of that. The change in temperature is proportional to the heat we add, and the change in temperature is inversely proportional to the mass. Okay? Give me a thumbs up if you're still with me. Still alive. Maddie, you're back. Can you hear me?
Yeah, I can hear you.
All right, good deal. Sorry about that. Okay, so there's one more thing we're going to worry about here. Let's suppose 2 cars pull up to the gas pump, and they both are on empty. Okay? So, Ozair, you got a 20-gallon tank, and all you got is 25 bucks. So all you can do is add 12 gallons. How much will 12 gallons fill up a 20-gallon tank? what percentage? Will it fill it up 100%?
No,
How much?
like 50%-ish.
A little more than 50, right? 12 out of 20 is
60%.
60%. So 12 gallons will fill up a 20-gallon tank, 60%, right? Now, Andres pulls up, and he's got a big old truck. Pretend, of course. Unless you really have a truck, Andres? No? Okay. Someday he's going to have a big old truck. He's got a 60-gallon tank. He also only has 25 bucks, so he can only buy 12 gallons. Andres, how much will the 12 gallons fill up your 60-gallon tank?
20%.
20%. So the same amount of gas has different effects on your gas meter, right? Your gas gauge in your car. If you have a small capacity tank, like 20 gallons, 12 gallons makes a big difference and fills you up 60%. So here's my little gauge. Fills up 60%. If you have a large capacity tank, the same amount of gas only fills you up 20%. So can you see that how much the tank gets filled, the percentage of change, is inversely proportional to the capacity? Small capacity tank, 12 gallons makes a big change. Big capacity tank, 12 gallons makes a small change. Does that sort of make sense in that context? Yeah? Okay. All right. So now let's go with that a little more. It turns out that there's an inverse relationship between the capacity of the tank and how much the fuel gauge changes. Okay? If the capacity is big, 12 gallons will have a small change. The same thing turns out to be true with substances that can hold energy, heat. Okay? All substances can store heat or energy, but every substance can store different amounts of energy. Some things like water are great at storing energy. Water can hold a huge amount of energy. It has a large capacity. Something like oil doesn't hold as much energy. It has a smaller capacity. So if we're going to add a fixed amount of heat, how much the temperature changes will depend on the capacity. If the capacity is big, we'll have a small change in temperature. And if the capacity is small, we'll have a big change in temperature. So here's part B of the lab, and this is kind of what yours should look like. I color-coded mine so my oil was yellow, because in the little simulator, the oil was yellow, but it doesn't matter. I think what you found was that you had two lines. They were both straight, and so we can conclude that the change in temperature is directly proportional to the energy added for both liquids. But there's a difference. A given amount of energy. So look at 30,000 joules there. Can you see the graph there, Lexi? When I added 30,000 joules of energy to the water, the blue line, what was the change in temperature? Just kind of ballpark it there.
The change in temperature?
When I added 30,000 joules of energy, what was the change in the temperature?
About like 18 or 19.
Yeah, a little less than 20. I'm not sure what it was, but you're exactly right. So adding 30,000 joules caused the water to heat up about 18 degrees. What did adding 30,000 joules of energy to the oil do, though? Can you see that, Maddie? We add 30,000 joules of energy to oil, the same amount of heat that we added to the water. What is the change in temperature of the oil?
Would it be about 50 or 45-ish?
I can't tell exactly, but yeah, you're right. See, so oil has a smaller capacity to hold heat. So the same amount of energy caused a bigger change in its temperature. Okay, does that sort of make sense? So every substance is able to hold different amounts of heat depending on how the molecules are arranged, how they can spin and vibrate and stuff, okay? So if we have a fixed amount of heat, if something has a small capacity, it means there's going to be a big change in temperature. And if it has a big capacity, we're going to get a small change in temperature. Okay? So all of that to say that there's this third variable. In the lab, we looked at the mass and we looked at the Q, the heat we added. But there's a third thing that matters, and that's called the heat capacity, okay? And the temperature is inversely proportional to it. You get bigger capacities, you get smaller changes in temperature. Now, these heat capacities, we're going to look up in a table. Can you guys see the table there? Take a look at it there. Oh, there? Which of those substances has the smallest heat capacity?
Gold?
Yeah, who would have thought? Gold has a very small capacity. If you look at the units up here at the top, you can see that is how many joules of energy it takes to make 1 kilogram of that substance get 1 degree warmer. So gold, it takes 129 joules to make a kilogram of gold 1 degree Celsius warmer. How much energy does it take to make water, 1 kilogram of water, 1 degree Celsius warmer? What do you think there, Lexi?
4,186.
Yeah, that's like 30 times as much heat as gold, right? That's a really big difference. So gold has the smallest heat capacity of all the substances there, and water has the biggest. What do you notice in general about things that are metal? Are the heat capacities big or small? Andres? Things that you know are metals.
They're smaller.
Yeah, they're a lot smaller than like water and ice, steam, things like that, right? Yeah, so the heat capacity of a substance is determined by the molecular bonds, and we're not going to worry about how that works. We're just going to look it up in a table. For water, the heat capacity is 4,186. That's how many joules of energy it takes to make 1 kilogram of water 1 degree Celsius warmer. Have you guys seen that number before? 4,186? It's a trick question. You've seen it before. Take a peek in your toolbox under your handy conversions. See if you can see a 4,186 laying around. Anybody see one? If you see it, unmute yourself and tell us where it is.
4,186 joules equals 1 calorie.
Yeah, we've seen that number before. It turns out that how much heat it takes to warm up 1 kilogram of water 1 degree Celsius, that's what we call the calorie. So since it takes 4,186 joules to do the same job, 4,186 joules is the same as 1 calorie. That's where we got the calorie from originally. We decided the calorie was going to be however much heat it takes to warm up 1 degree Celsius, 1 kilogram of water. Okay? So that's where it came from. So you guys have seen that before. All right. So a couple of other notes. Just be careful when you're solving problems. The heat capacity of ice is different than the heat capacity of water, which is different from the heat capacity of steam. So make sure when you're solving a problem, if I tell you it's ice, don't use 4,186, okay? Make sure you have the right phase, solid, liquid, or gas. Metals don't have any large heat capacities. They are really good at conducting heat, but not at storing heat. So metal feels super hot because when you touch it, it can pass its heat along to you really quickly. It's good at conducting it, passing it along. It's not very good at storing lots of heat. And we're not going to worry about gases, so we don't need to worry about that last one there, okay? All right, so based on our experiments in lab, which we're going to finish here in a little bit, we can say that the change in temperature of a substance is proportional to the added heat. The more heat you add, the more the temperature goes up. We can say that it's inversely proportional to the mass. The more mass you have, the smaller the change in temperature. And it's inversely proportional to the heat capacity. The bigger the capacity, the smaller the change in temperature. So those three ideas should sort of make a little bit of sense to you. Just kind of from our lab investigations. Now, don't write this down yet, okay? Here's what we get when we put it all together. The change in temperature is inversely proportional to the mass, so the mass is in the bottom. It's inversely proportional to the heat capacity, so the heat capacity is in the bottom, and it's directly proportional to Q, so Q is in the numerator, the top, okay? Now, we don't usually write equations like this because we don't like fractions. So if I multiply both sides by m times c, I can clear the fraction and I can get this form. And that's what I want you to put in your toolbox, okay? This tells us the relationship between these four things: the heat, Q, the mass, the heat capacity, and the change in temperature. So jot that in your toolbox. All right. You good, or you need another minute? Give me one finger up if you need another minute. Oh, okay. All right. Andres is good. Lexi, you good? Addie, you good? All right. So let's solve an example problem, okay? So I want to know how much heat is going to be required to warm up my water from 20 degrees. So what I want is a nice cup of tea. You guys see me drinking tea every day? Tea is my favorite thing because I grew up in a British prep school. We had tea every day instead of recess. Anyway, I want to warm up my water from 20 degrees Celsius, which is room temperature, to 95 degrees Celsius, which is perfect for a cup of tea. I want to know how much heat it's going to take, okay? So what are you going to use for the heat capacity? Look at the table there, and help me out there, Maddie. What are we going to use for the heat capacity?
Do we use the water?
That's it. It's water, right? So we're going to use 4,186 for water. So our solution is going to look something like this. First of all, we're going to make a little diagram. In our diagram, we're going to show the change in temperature as we add energy. The reason we make diagrams like this is because later we're going to modify them somewhat when we do what are called phase changes, okay? So just kind of get in the habit of, when you think about a problem, you can draw a microwave and a cup, but the part I really care about is a little graph. What happens is you add heat, the temperature goes up, okay? The heat capacity, we're going to use 4,186, as Maddie pointed out. Take a look here. What are the units for the heat capacity? Well, the units for heat capacity are joules per kilogram degree Celsius. That tells us what units we have to use to solve our problem. If I give you the temperature in Fahrenheit, you got to put it in Celsius because that's what we need. If I give you the energy in calories, you've got to convert it to joules. Because this is the unit for our table, that's the unit you have to use, okay? All right, so here's our variable list. Everybody agree with that? Look it over. And so to solve this problem, it's going to be pretty easy. We are simply going to evaluate Q equals MC delta T to find Q. I'm going to plug in my numbers, grab my calculator, and you get 75,000 joules. Now, this is a good idea to know because my microwave is 1,000 watts. My microwave adds 1,000 joules every second. So how long should I microwave my water to get it to 95 degrees? Was there?
75 seconds.
There you go. You can figure it out. How do you guys microwave things? You probably do, whoops, got a bell. You probably do 30 seconds and you stick your finger in it. Not hot enough. You do another 30 seconds, stick your finger in it. Ouch, just got burnt. See, this way you can just calculate. If you know the heat capacity of maple syrup and you know the mass of your bottle, you could just figure out exactly how long to microwave it, right? There you go. That's a physics problem for tomorrow morning. Tell your dad to make you pancakes. You got to do a physics experiment. All right. That is the kind of problem we're going to solve. Okay, you'll be solving for one of these four things: Q, M, C, or delta T. And then my note at the bottom there, just a reminder that you got to make sure your units are all consistent. Okay? Okay, that's it for today. So we have about 45 minutes. And what I'd like you to do is do part C of the lab from yesterday. Change the mass. Just go like 0.1, 0.15, 0.2, 0.25, 0.3, 0.35, and 0.4. Okay? And for each of the masses, measure the heat change, make a graph, put it on there for part C, and then finish that up. And then when you get that done, there's some problems to solve using Q equals MC delta T. All right? That's the job for today. So I'll put you guys back in your breakout rooms so that I can check in on you and you can talk to each other if you need to. So finish up the lab and then move on to the problems. Okay? Should see an invitation to a breakout room there. Is there?